What if I told you there's a hidden mathematical code, a code that's embedded in literally everything, from the music you stream to the video games you play, and yeah, even in the satellites that are orbiting our planet right now? Well, today, we're going to crack that code.
Now, I promise you, this is not your high school math class. Forget the dusty textbooks. We're going to uncover where this incredible tool shows up in the real world, often in places you would absolutely never expect.
I mean, just think about your favorite video game for a second. How do the developers build those huge, immersive, realistic 3D worlds basically from nothing? How do they tell a computer exactly where to put every tree, how light should bounce off a surface, or how your character can even move through that space?
Well, the answer is kind of wild, because it connects all of these different fields. It's the key to making digital music, to investigating a crime scene, to navigating our entire planet. It all comes down to one thing: trigonometry.
Okay, so let's dive into this. To really understand how it all works, we have to go back to its core idea. And trust me, it's incredibly simple, but wow, is it powerful.
The word itself, trigonometry, sounds pretty intimidating, right? But the ancient Greeks who named it were actually super literal. Tri means three, gon means sides, and metron means measure. That's it. Three-side measure. It's all about the relationships inside a triangle.
And this idea, it's ancient. We're talking over 2,000 years ago. It got its start with early astronomers who were trying to figure out how to measure the distance to the stars and planets. And from there, it just took off, spreading into pretty much every field you can imagine. So, the main character in our story today is the right-angled triangle. Now, if we pick one of the other angles to focus on, let's say this one right here, the sides all get special names. The side way across from our angle, that's the opposite. The one right next to it, that's the adjacent. And that long, slanted side, which is always opposite the right angle, is the hypotenuse. Just by understanding the relationship between these three sides, we suddenly unlock this sort of secret toolkit. It's got three simple but super powerful tools that let us find any unknown length or angle we want, as long as we have a couple of clues to start with. Our first tool is called sine. All sine is a ratio. It's the length of that opposite side divided by the length of the hypotenuse. And here's the incredible part. For any given angle, say 30 degrees, that ratio is always the same. It doesn't matter if the triangle is tiny or absolutely massive. That fixed relationship, that's the secret sauce.
Next up, we have cosine. You can think of it as sine's partner in crime. While sine connects the opposite and the hypotenuse, cosine gives us the fixed ratio between the adjacent side and the hypotenuse. You put them together, and you have these really powerful ways to link an angle to the two longest sides of a right triangle.
And our third key tool is tangent. Now this one is special. It connects the two shorter sides directly, the opposite and the adjacent. And as it turns out, it's the exact tool we're going to need to solve a real-world problem.
All right, that's enough theory. Let's see how these tools actually work in practice. Let's build from this simple idea into something that can, literally measure the world around us.
So, here's our problem. We've got this building, and it's way too tall to measure with a tape measure. But we do have two clues. We know exactly how far away we're standing from its base, and we can measure the angle from where we are on the ground all the way up to the very top.
Okay, let's lay out the facts, just like a detective. What we know is we're 90 feet from the base. We look up, and that angle of elevation is 35 degrees. The only thing we don't know is the height of that building. So, time to open up our toolkit. Which tool connects the height, which is the side opposite our angle, with our distance on the ground, the side that's adjacent to our angle? Opposite and adjacent? Yep, that has to be tangent. So the tangent of our 35-degree angle equals the height divided by those 90 feet. And this is where the magic happens. We just rearrange the formula a little bit, do a quick calculation, and bam! The height is 63.018 feet. We just measured something impossible without ever leaving the ground. How cool is that?
So here's the crucial point. This is not just some neat trick for measuring buildings. Once you know this code, you start seeing it written absolutely everywhere.
Take aviation, for example. Pilots are constantly using trigonometry to figure out their actual flight path, by calculating their own speed and direction against the speed and direction of the wind. Criminologists use it to work backwards. They can calculate the trajectory of a projectile, like a bullet, to reconstruct exactly what happened at a crime scene. It's a fundamental tool in forensics. Get this,
Even marine biologists use it. They can estimate the size of enormous animals like whales from a distance, and even calculate how deep sunlight goes into the ocean to support life.
And it's even more fundamental than that. The sound waves that are carrying my voice to you right now, the light waves coming from your screen, all of them are described perfectly by sine and cosine functions. It is literally the language of waves.
So it's no surprise then that over a century ago, the philosopher J.F. Herbart wrote this: "Trigonometry really does sit right at the center of how we apply math to understand the real world."
So really, what you should take away from all this isn't just a couple of formulas. It's a completely new way of seeing things. The world isn't just made of objects. It's made of relationships and angles and triangles.
I mean it, from the pixels on this very screen to the support beams in the ceiling above you and the path a satellite takes across the night sky. Our modern world is quite literally built on triangles. So the only question left is, now that you know the code, what triangles are hiding in plain sight all around you?